Hello, Mr. Betts here. Let's take a look at an optimization problem where we are engineering a can, an aluminum can that's going to hold a soft drink. It's going to be a 12-ounce can, but for the purpose of our problem, we're going to use milliliters. One convenient thing about the metric unit system is that a milliliter is equal to a cubic centimeter. So instead of milliliters, we're going to think of this as cubic centimeters. And we're going to make it a cylinder, and we're going to idealize this problem. So it's going to have straight sides. It's not going to have the lip at the top and the indentation at the bottom, like we would have in a normal soda can. I do want to point out that we're trying to minimize the amount of aluminum used, and that's kind of a proxy for the amount that it's going to cost us to make the can. So minimizing the aluminum is one way to minimize costs, but also because we have to manufacture the top and the bottom a little bit differently, it's not exactly going to be right. So we are going to get an answer that looks a little different than the typical soda can that we're used to. But what we're looking to do here is just minimize the amount of aluminum used. Okay, we're not necessarily trying to minimize costs. So what dimensions, so what height and radius for this can are we going to get to the nearest tenth? Let's make that thousandth, since we always do thousandth, to the nearest thousandth of a centimeter, so that we minimize the amount of aluminum. So we have a picture here for our model, but we need to throw in some variables. So one variable is going to be the radius of the cylinder, and another one is going to be the height of the cylinder. And both of these are going to be variables that could range from 0 to really big numbers. So if the radius is really big, the height is going to be really small. On the other hand, if the height is really big, the radius is going to be really small. So the domains of each of these variables will be really any positive number. So we need to write a function for what we're trying to minimize. We are trying to minimize, in this case, the surface area. So the amount of aluminum we use is directly proportional to the surface area. In fact, it is the surface area times whatever the thickness of the aluminum is. So the surface area here is going to be, so we have a circle on the top and the bottom. So area of a circle is pi r squared, and there's two of them. And then the lateral surface area, the side of the can, is going to be the circumference of the top, or circumference of the bottom, 2 pi r times the height. Okay, so think of this as if we just slice the can down the side and unroll it, we're going to get a rectangle, and that rectangle is going to have a width of 2 pi r and a height of h. Now, the surface area equation is written mostly in terms of r, but we do have h in there. We need to write this in terms of a single variable. So we're going to use a relationship given to us in the problem here that the volume should be 355 cubic centimeters. So the volume of a cylinder is going to be the area of the base, pi r squared, times the height, and that needs to be 355. Since I want to eliminate h here, I'm going to solve for h here, and we get h equals 355 over pi r squared. And we're going to plug that in here for h, and we get surface area is equal to 2 pi r squared plus, so 2 pi r times 355 is going to be 710 times pi r over pi r squared. So the r's are going to cancel, the pi's are going to cancel, and we get 710 over r. Now we want to take the derivative. So we want to figure out the candidates for when the amount of aluminum we use is going to be the smallest. So the surface area, the derivative of the surface area is going to be 4 pi r. And then this is 710 r to the negative 1. So it's going to be negative 710 r to the negative 2. And we want to know when that derivative is either equal to 0 or undefined to find critical values. The derivative will be undefined when r is equal to 0, but keep in mind that r is not equal to 0. That's not in the possible values of r that we established early on, so we don't need to identify that as a candidate. We do want to figure out, though, when this is equal to 0, And so we're going to get, when we solve this, we are going to use our calculator because this is a calculator problem. So we're going to plug into our calculator this derivative. We do want to make sure we write on our paper that we're setting that derivative equal to 0. So this is the equation that we're solving. And then if we graph this equation, I do want to point out that we're putting the derivative in here for y1. When I used Zoom Fit, as r approaches 0, the derivative is really big negative number. In fact, it's going to be a vertical asymptote there. So when I did a Zoom Fit, my y min ended up being a huge negative number, and the graph was not very useful to me. So after the Zoom Fit, I went back and I changed my y min to negative 35, just kind of an arbitrary value. It matched pretty closely to the y max. It doesn't matter what you choose there, but just something so that our picture is a little bit better. And then I use that to find the 0. So our derivative is going to equal 0 at this x value. And if I want to justify that this x value, which remember is actually an r value, is going to give us a minimum amount of aluminum used, I'm going to use the fact that the derivative of our surface area is negative to the left of 3.837, and it's positive to the right. So our surface area is decreasing as the radius gets closer to 3.837, and then it starts increasing beyond. I also want to point out that, I should have mentioned this earlier, I made my X max 5. That's also kind of an arbitrary choice. I just chose something that I thought would be bigger than the actual value we're looking for. Remember, X could be a really big number. X could go to infinity. So it would probably be a good idea to take a look at this picture and make sure it doesn't decrease and cross the x-axis again, because that could give us some issues, but that doesn't happen here. So answer the question. In order to answer the question, we have the radius, that's going to be the x, but we also need the height. It says the height and radius. So since I'm going to use the radius to get the height, I want to store that value into the calculator and then use that to figure out what the height is going to be. Remember, we have a relationship that is the height equals 355 over pi r squared. So I'm going to take this value and plug it into that expression to figure out what the height is. And I'm going to use the calculator's memory to make sure that's as accurate as possible. So I stored the 3.837 number in for r. You could store it for any variable. I chose r since that's a radius. And then I plugged that into the expression to figure out what h is. So the minimum amount of aluminum used will be when let's say r equals 3.837 centimeters and h equals 7.674 centimeters. And then remember, we need to justify using calculus. So in this case, we're going to say because the surface area is decreasing to the left of r equals 3.837 and increasing to the right. Now, I do want to point out that this problem does not tell us to justify. It's always better to, as long as we're not saying anything incorrect, it's always better to include a little bit more and give a reason for our answer, even if the question doesn't ask for it. Especially, it's better to do that than to leave that off when we are asked for it. Keep in mind that these are calculus problems, so regardless of whether you're actually writing out the justification, the process needs to include calculus. So when we're doing these optimization problems, Do not just plug in the function that we're trying to optimize into your calculator and use your calculator to find a maximum or minimum, because that will not get you credit for me, and it will also not get you credit on the AP test.